Hello, everyone, and welcome to a new EurJOC virtual symposium. I'm Nijs. I'm the journalist editor-in-chief, and I'm excited to have this special edition of the EurJOC virtual symposium series happening today. And we're honoring the outstanding work of Larry Overman, and we're also celebrating the launch of his autobiography, which was published as part of the Lives in Chemistry book series. Some of you might know or not know this, but EurJOC is actually a society journal belonging to Chemistry Europe. It was launched more than 25 years ago through the merger of several national European society journals, and among them was also Liebig's Annalen, so that's the journal of the German Chemical Society. And as such, it made perfect sense to team up with the Lives in Chemistry team, which also on this book series is also published on behalf of the German Chemical Society, namely the Division of History of the German Chemical Society. And of course, then to promote and also celebrate the launch of Larry Overman's autobiography. I'm very proud to have Larry here with us today, and he will give us some insights on the book, on the process of writing the book. And we also have two of his former colleagues presenting, namely Martin Oestreich from the TU Berlin. He is a former postdoc of Larry Overman and also a member of the Lives in Chemistry board, and also David MacMillan, who's a former PhD student of Larry's. I think they will both share some insights into of their time they had together with Larry, and of course also present their scientific research. Together with my colleague Pilar, I'm really happy to guide you through the symposium today. I will introduce the speakers together with her and also take care of a few technical things. As this is an honorary symposium, we decided not to do a question and answer session after the individual talks. And with this, I will now start by introducing, let's just say our guest of honor, so Larry Overman. Larry received his bachelor in 1965 at Earlham College in Richmond, Indiana. He then moved to the University of Wisconsin in Madison for his graduate studies, where he worked with Professor Whitlock on his dissertation. In 1969, he moved to Columbia University as a postdoctoral fellow, where he worked with Ronald Breslau. Larry began his independent career at the University of California, Irvine in 1971. And at that time, the campus at Irvine was actually quite young, so only 6 years old. He remained at UC Irvine for 50 years, where his research interests centered on the invention of new transformation and strategies in organic synthesis and the total synthesis of natural products. He closed his laboratory a few years ago in 2021, and he's still an emeritus professor at UC Irvine. 90 PhD students and more than 200 postdoctoral fellows trained in Larry Overman's lab. And we have two of them here with us today. And I've also noticed on the registrations that some are among the audience, so welcome. He has won many awards, including the Arthur Cope Award in 2003, the Tetrahedron Prize for Creativity in Organic Chemistry in 2008, and the Roy Noyori Prize in 2015. And with this, I would like to officially start the symposium and then pass on to Larry, who will give us some insights on the progress of writing his book. Thank you.
Well, thank you, Anne. It's a delight to be here. What I wanted to do is just say a little about what led me to what my objectives were in writing this book. And I can't see the whole screen here, so let me modify this a little. So what I describe here is just that my hope in writing this account was to communicate really how discoveries take place and how vibrant and interdisciplinary a research group in organic chemistry is, with people of various different ages, maybe even a high school student to undergraduates to graduate students and postdocs. I also wanted to point out that my life's research was not directed by any grand plan. It evolved very much as we did it in the laboratory, very much experimentally derived. And many of our directions came about by unexpected results. So one of the key things I wanted to do, maybe a somewhat unusual in an autobiography, is I wanted to really speak also to young chemists. And besides relating just my scientific journey and one, slice of research during my lifetime, I hope the book would speak to young people that are considering a career in academic organic chemistry, because I want to discuss in some detail in the book some of the issues I faced and how I maybe stumbled through them and dealt with them. And if I could have the next slide, I'll just mention a few of these. So I think in an academic career, there are a number of decisions you face. Maybe the one of the early ones and an ongoing one is what area you're going to work in. And I think there are two fundamental choices here. You either work in a popular area, which has great advantages and there are a lot of people in it, maybe there's more money in it, or you work in a fringe area and if you pick a fringe area, there's maybe not as much competition, but if it remains a fringe area, that's not good. If it becomes a major area, then you've really struck gold. How to mentor is something that it took me a number of years to develop. I learned a lot about this largely from my students educating me. And then in our latter parts of my career where total synthesis was a major focus, I think choosing how you choose total synthesis targets is an extremely important part of the job. Another thing that I thought was very important is how you balance work and life. Family is something that was very important to me, and chemistry was certainly my hobby, and I think to be an academic chemist has to be your hobby, but I don't think it has to be your only hobby. And I certainly had a number of other found it essential to be away from chemistry and at a number of times to refresh my mind. So if I have the next slide, I just want to, again, speaking to, if I get the next slide, please. Speaking to the younger audience, I just wanted to say something about how satisfying I found the career. No, if you go back one, please. Pilar, could we go back? Yeah. So, obviously one nice thing in academic research is you can largely, if you can fund it, pursue the opportunities that interest you. I think the greatest joy, though, is really to do it with young coworkers, particularly people that it's a really decisive time in their career, and their excitement, observing them develop and prosper is something that I took enormous pleasure from. And I just wanted to conclude by saying I think the pleasure in leading a research program is not only from the great discoveries you make or the completed total syntheses, but it's really what you learn along the way. And I took enormous joy of just finally understanding something I didn't before, or when an experimental result turns you a different way. So let me conclude there. I'm going to happily pass this on to Martin to carry on, who will tell you more about the Lives in Chemistry book series. So could I have the next slide? Have a few people to thank. My more than 300 coworkers are the ones I really predominantly need to thank. They made most of the discoveries, almost all the discoveries made in my lab possible. This book itself wouldn't have appeared if it wasn't for the really wonderful team at the Lives in Chemistry group. Peter and Martin assisted me in early review of chapters, and Eva and Ralph in the production of the book. I also today want to really thank Nijs and the European Journal of Organic team for putting on this event. And then I certainly have to thank Martin and David for joining me on this occasion. Thanks a lot.
Thank you, Larry, for your presentation. And it is my pleasure now to introduce the next speaker of today's event, Professor Martin Oestreich, So he received his diploma degree with Paul Michel in 1996, and then his PhD with Dieter Hope in Münster in 1999, if I'm correct. After 2 years of a postdoctoral stage with Professor Overman in the US, he completed his habilitation with Rainer Bruckner at the University of Freiburg in 2005. And then after that, he was appointed as Professor of Organic Chemistry at the University again of Münster. In 2011, he moved to the Technische Universität in Berlin, where he's currently working as a full professor, and his research focused mainly on silicon and synthesis and catalysis. So he has received a number of awards and scholarships to date, just to name a few of the latest ones: Walker Silicon Award or Boehringer Ingelheim Lectureship, for example. He is also part of a number of editorial boards, including the one of this book series, Lives in Chemistry. And also he works as an editor in several team titles. So Martin, please, the floor is yours.
Well, thank you, Pilar. Before I change to my screen, you can hear me, I guess. And now let me share my screen with you, hoping that you do. Do you see my screen now?
Yes.
Yes. Yep.
Perfect. Okay, so let me get the panel out of the way here. It's a bit confusing. It's going to work. Okay, so I guess you see my screen. I changed to the laser pointer. Okay, so the problem, I guess, with this presentation is that I cannot see anybody, only my slide, but I guess that's going to be fine. So before I say a few things, a few words about lives in chemistry, I'd like to echo what Larry just said. Thanks to Nijs and Wiley for setting this up in Larry's honor, and also to promote Larry's biography. And Larry's biography is, in fact, published as part of a rather young series entitled or called Lives in Chemistry. And I happen to have the pleasure to be on the board of that series. I didn't join in 2015. You can see, maybe you cannot see all the details because it's rather small, but you see the time beam here. And the whole story started in 2015. And I did join somewhat later down the road after the first 3 titles had actually been already published. And then Peter Güllis and Carsten Reinhardt approached me to join. So it started 2015 when Günther Meyer, professor of organic chemistry, retired professor of chemistry at the University of Gießen, decided not only to write his biography, but he handed this over on June 6th. You can see this little photo here. That's Professor Meyer. He handed his manuscript over to his former graduate student, Karl Reuter. And Karl Reuter is a founder of a chemical company and owner of a chemical company that has been in Freiburg for almost 30 years. At some point in these first couple of years, he made that important decision that he would sponsor a book series, starting with the biography by his PhD advisor. And the only boundary condition, I think this is quite unique and quite special, the only boundary condition that Karl had is that these biographies that we were going to publish would not be a simple collection of or let's say only a success story where people would simply give examples of how successful they have been in their professional life. The boundary condition is that the creative process needs to be obvious, and the authors should write their biography always having the creative process in mind. So it's about how projects evolved, how projects developed, and how maybe seemingly very different or deceptively different projects are somewhat connected to each other. So this is the only boundary condition. And other than that, authors are completely free how they write it and what they actually present in their biography. It took a few years of setting up the advisory board. The chair of or the chairman of our board is Carsten Reinhardt. You see him down here, and also here's a small photo. He's a professor of history with a focus or emphasis on chemistry. So he has a chemistry and history background, and he then put together this board. And first invitations were sent out, and we had the first people, first eminent chemists agreeing to write, and we published in 2021 the first 3 books, and after that in 2022 2 more books, and then we somehow got into the flow because we had in 2023 3 books published, and we do have funding and sponsoring for 3 books per year. 2024 we also have 3 books. So Larry's book is the first this year, and we will have the biography of an eminent inorganic chemist, Professor Schmidbauer from TU Munich, and we will also have Professor Njori's biography published towards the end of this year. And also for next year, we already have 3 books in the pipeline. Professor Eschenmoser sadly passed away recently, but we have the honor of publishing his biography. Sigrid Payr-Imhoff, eminent computational chemist, will have her biography out next year. And I think Professor Kurse-Höhinghaus, also that manuscript will be published towards the end of next year. And Klaus Möhn's manuscript is already accepted, maybe then for 2025 or 2026. So you see this whole thing is now, and we have a few more manuscripts in the pipeline, is evolving quite nicely. And I can only say that all board members, I guess I should give the names real quick. So you see Peter Görlitz here, Dieter Jahn, former BSF, just joined the board. Eva Wille, former Wiley, is a part of the board. Katharina Fromm was invited to join together with me. She's in Fribourg. And Henning Hopf from Braunschweig is also a member of the board. And Ralf Hahn, he has been mentioned before by Larry, is the publisher, but he also has a chemistry background and a strong background in history of chemistry. So it's always very insightful to discuss with him and the other board members about the manuscripts and also how to proceed with further invitations. So far, maybe I move on to the next slide. We've published these beautifully looking books, and this has been recognized by an award recently, a gold medal, as you can see here, for the design, at least for bibliophilic people. This book really is beautifully done. I have a printed copy here in my hand. I cannot see myself, but maybe you see me holding that copy. And it looks great from the outside, and the inside is even nicer. It's really perfectly designed. And maybe I move on to Larry's biography. Here you see his cover. And I have to say, Larry, it's been a pleasure to work with you on this. I think Peter and I had expected that this is going to be a smooth process. You are just a fantastic writer. One can already get this from all your published papers, and your biography was also perfectly written, pleasant to read. I think we had just very few comments on the manuscript, and so the whole process, I think, in total took 1.5 years, maybe slightly longer because of the publishing process. But the manuscript writing and Peter and me looking at your manuscript didn't take very long. So you were totally reliable, and you delivered as promised and as expected. So thank you for that. It's been a pleasure to do this with you. And of course, this is a QR code, and I cannot see anybody smiling, but I guess you know what that means. Of course, these books are not designed to be big bestsellers, and they're not. The whole project is not designed to make money. But of course, we will be very happy if we sell a few copies. And for those in the audience who are really interested, because it really is great reading also for the young generation, as Larry just mentioned. You can quickly pick up your cell phone before you put it back on the desk and scan the QR code and maybe place an order while I give my, or place an order now, or while I give my scientific talk. Okay, I can leave this on for a few more seconds. Maybe we can monitor how many copies got ordered while I give my talk. Okay, let me continue with the final, and it's also in the color that Larry's cover is. Yeah, the color is a big theme in these books. So in that magenta, or I don't even have an English word for this color. I don't even have a German word for this color. So there's a certificate Urkunde that I'd like to present to Larry. Ideally, I would have handed this over in person, but this is not possible right now. So you will receive this soon by regular mail. It is signed by Professor Carsten Reinhardt, the chairman of our advisory board, and also by Stefan Nijs, who is the current president of the German Chemical Society. So you can see we take this project really seriously. And I think this is an important project to maintain also yeah, the history of chemistry and how eminent chemists have shaped their academic careers. So Larry, this will be in the mail to you soon. Okay. So let me start now with some chemistry. I've been a postdoc with Larry from 1991 until 2001, and my chemistry of the initial plan was that I would work on a complex alkaloid. Larry was interested at the time in a family of alkaloids, pyrroloindolene or polypyrroloindolene alkaloids, very complex structures. And my task was to tackle a tetrameric member of this family. I didn't put it here on a slide because I didn't finish that molecule. So I didn't become a finisher in Larry's lab, but the beauty of these molecules is not only their symmetry, but also that they contain 4 quaternary carbon atoms. And this has been a theme in Larry's lab to construct quaternary carbon atoms, especially by the intramolecular Heck reaction introduced by Larry to make this important structural motif. And you can see that motif up here, oxindoles having a fully substituted carbon atom, asymmetry substituted carbon atom in the benzylic position, so to speak. And so as part of my efforts to at least get a part of the molecule done, I made a discovery, a serendipitous discovery, that the Heck reaction that I was supposed to do, or that I wanted to do on a modified substrate, just didn't go to completion or didn't work. And then eventually proposed and also isolated an intermediate of a Heck reaction, which is a sigma alkyl palladium species with stereochemically or conformationally accessible beta hydrogen atoms. And this molecule just would not undergo beta hydride elimination. And I think at the time, this was the first example of an isolated intermediate after migratory insertion of a Heck reaction. And that made it a bit of a special discovery. Also, it helped understanding the Heck reaction of these systems, because in the end, it depended on the base used in the Heck reaction and the conjugate acid that would eventually protonate here and then get the reaction to completion. So this is what I did in Larry's lab. And Larry was so kind to allow me to dedicate that angewandte paper to the 60th birthday of my PhD advisor, Dieter Hoppe. And it's a bit sad. I dedicated another paper to Dieter Hoppe, my dear PhD mentor, because he sadly passed away earlier this year. And this is the angewandte paper that I did dedicate to him in his memory. He's been a really friendly and polite and just a fantastic person and a great PhD advisor. You can see also from this that, as mentioned by Pilar before, we are mainly involved in silicon chemistry or main group chemistry related to inorganic aspects and to organic aspects, and also related to catalysis. And when I was in Larry's lab, of course, I started to feel the pressure also of writing proposals for my independent career, and I spent a great deal of time in well, this is 2000 and 2001. This was a time when we would still go to the library, in fact. So I spent a great deal of time in the library of UC Irvine, and I just started reading. I had some ideas in the back of my mind, but while looking at books and well, in the end, I stumbled across a book by Leo Sommer, I guess almost forgotten eminent silicon chemist, who had been looking into the fundamental aspects of chirality at silicon. And so my initial thought was, why not entering this field? Larry has just mentioned that there is a danger of entering fields that are not crowded with other colleagues, but of course fields that are well, when I was the only person, basically almost the only person in the world to start this chemistry, and so this is how I entered silicon chemistry. And we did some work on chiral silicon or chiral silicon compounds, and this was then the starting point that opened the door to many other aspects in main group chemistry and silicon chemistry. But I remember going to Larry's office and asking him to look at a rough draft of what I intended to do, and I told him that it's not going to be total synthesis but silicon chemistry. And his supportive comment, I have to say, was that no, not everybody has to do total synthesis, and it's not wrong to start something new. And I'm actually looking back quite happy that I made that decision to start some new chemistry that at that point in time absolutely nobody was interested in. So I hope I can interest you with what I'm going to share with you today, which is some recent chemistry from my laboratory. And the title summarizing these recent efforts is the cation shuffle. And I hope towards the end of the talk you will understand why this talk has this maybe a funny title. So let me start. It's going to be about cations, and I'd like to start with a little question or a little riddle. I would not have been able to predict the outcome of the reaction of tetramethylsilane, pretty inert, benzene, methyl chloride, and a trace of a Silylium ion. You will see soon the outcome of this is, but I'm totally honest, maybe even 3-4 years ago, I would have not been able to predict the outcome. It's a very clean reaction, actually, the outcome of this reaction, and it is actually quite a useful reaction. So let me start with how we entered the field of Silylium ion chemistry. Roughly speaking, 15 years ago, I became interested in silicon cations and Silylium ions. So Silylium ions are very different from carbenium ions. The carbenium ions do have a long history. The triple cation is a long-known species, and I think the work of Hans Meerwein and George Olah is known to everybody. But Silylium ions do have a bit of a rougher history, and it's only some 25-30 years ago that there was considerable progress in isolating a Silylium ion and fully characterizing a Silylium ion in the condensed phase. And this is mainly due to the outstanding work by Joe Lambert at that time at Northwestern University, and also Chris Reed contributed to this development quite substantially. I will get back to Chris's work later in my talk. So they eventually got the molecular structure of a Silylium ion. It's especially this one, which can be obtained in free form, because this is really a strong Lewis acid. And the 6 mesotyl groups, or more precisely the 6 methyl groups, they sterically shield the empty orbital at the silicon atom in such a way that no Lewis base can coordinate. Now, nowadays, with today's salesmanship, one would call this a frustrated Lewis acid, but it's so frustrated that it doesn't do anything. So this is a bit of a dead end when it comes to further applications. In 1995, even before that seminal science paper, but there's a work before by Lambert published in Science. In 1995, Lambert published a review in Chemical Reviews, only 11 pages long, that summarized all the modern approaches to Silylium cations. This is how he called it at that time. And 11 pages is not a lot. So we published a ChemRef in 2021, and we only finished that nightmare review because of the pandemic, because we eventually had time to wrap it up. This was done together with Thomas Müller, inorganic chemist from Oldenburg, an expert in the inorganic aspects of Silylium ions in silicon chemistry. So this is really comprehensive, I guess, but it's 100 pages. So you can, and this is not meant to show off that we eventually managed to finish a big review, but it just shows that the field has tremendously grown over the last, let's say, 10 years. And this is not only because of our work, but also because of the work of others who have now rediscovered that Silylium ions can be of some use. So the first thing that we decided to do in Silylium ion chemistry was to make use of Silylium ions as super strong Lewis acids to achieve new catalytic Lewis acid catalyzed reactions. And the project was taken over and started by my first master's student in Münster, my second grad student in Münster, Hendrik Laren. He's still in my lab. He did a postdoc with Brian Stolz, and he's now permanent researcher or senior scientist in my lab. He's basically also a professor, and he started. You can actually see how he looked in the early days. Later on, you can see that he also has gotten some gray hair already. The idea was to tame the Lewis acidity of the Silylium ion by attaching a ferrocenyl backbone to the silicon atom. And the electron density that the ferrocene would offer would maybe tame but not quench the Lewis acidity of the Silylium ion. So we had to make that funny molecule, and we didn't draw the molecule the way it's shown here in the beginning. This comes from subsequent studies, but we were able to make that molecule. Chemical shift is exactly where we had expected it to be. But we learned that with this counter anion, these species are notoriously difficult to crystallize, and we had to change the counter anion to a mutates type it's a dianion, so it's a boronate anion. So this boron cluster is quite useful for that. And we eventually managed to crystallize that molecule. This is old stuff, so I will be quick here, but I love this structure so much that I really need to show this in all of my Silylium ion talks, because you can see that the silicon atom is indeed trigonal planar, as you would expect for a Silylium ion and also carbenium ion, despite the interaction with the ferrocene backbone. So this dotted bond is a bit misleading, and this is put in by the crystallographer. So this is not entirely true. But the silicon atom is so electron deficient that it needs the electron density from the ferrocene backbone, and this is reflected in this crazy bonding situation at the C-ipso carbon atom. I cannot even tell what hybridization that would be, so it's certainly not sp2 anymore. What's also interesting is that the positive charge is in fact residing at the silicon atom. These are the electrostatic potentials computed by Stefan Grimme. So blue stands for positive charge, and it indeed is a silicon Lewis acid. And here comes the electrostatic potential for the related carbenium ion. So here should be the carbenium ion. It's a long known molecule, and it is not blue at the carbon atom. So it's a fully delocalized system, and it has been long known that the carbenium ion has a fulvene type structure and is not a carbenium ion Lewis acid. And so the Silylium ion is distinctly different from the carbenium ion. So we went on to do some catalysis with these molecules, and we made a whole family of these ferrocene stabilized Silylium ions. I just show you on one slide what we've done, what we achieved with this. So we needed to find a model reaction to demonstrate the power of this Lewis acid, and we decided to do or to look into Diels-Alder reactions, also because of their cleanliness and they're easy to do reactions. But when people probe or test their Lewis acids in Diels-Alder reactions, they always use cyclopentadiene. And this is a bit cheating because cyclopentadiene reacts with almost anything, including with itself. Whereas cyclohexadiene is far less reactive, 500 times less reactive. And there are not so many of these other reactions with cyclohexadiene known. And in fact, the enones, particularly chalcone and the cyclic enones, are really nasty dienophiles. And for those two, there had not been even reported reactions. And we can catalyze these reactions at -40 degrees with our silylium ion, or the silylium ion that we developed. -40 degrees is, of course, an inconvenient reaction temperature. This is only to demonstrate the reactivity of the Lewis acid. Depending on the solvent one chooses, one can go to higher temperature and it works equally well. We then went on with this chemistry to develop an asymmetric version of this with, I'd say, limited success. And I don't want to spend too much time on this. So we had a few years struggling with the asymmetric version. But over the course of these years, we of course thought about other applications and other reactions that one could do with silylium ions. And now I'm jumping a little bit in topic, but one of the things that we of course came across is that can we do electrophilic aromatic substitution with silylium ions? Why is there no Siler-Friedel-Crafts reaction or Friedel-Crafts silylation in any organic chemistry textbook? So the same is true for the Friedel-Crafts type O relation chemistry. So why are these reactions missing in the literature? Now the problem is that the Siler-Friedel-Crafts reaction, which is the forward reaction going from here to here, is a sluggish reaction because it's reversible, and the backward reaction is so much favored. And most people, I guess also in the audience, have only done a proto-dearylation or a proto-desylation of an arene as part of a Tamao-Fleming oxidation. So by the addition of acid, by the way. And so the backward reaction is what's quite popular in synthetic organic chemistry, whereas the forward reaction doesn't really work. The Friedel-Crafts alkylation is also a reversible electrophilic aromatic substitution. However, one can easily make the products and they're actually quite stable. And the backward reaction is relatively slow. Of course, one can, if this is a t-butyl group, one can take off the t-butyl group by treatment with acid, and the t-butyl group can be used as a protective group on an arene. So it is doable, but the backward reaction is certainly not that facile. And it was Simonetta Fornarini from Rome. She's a mass spectrometrist and also a computational chemist. She looked into this. This is now quite a while ago. And one explanation is that the Friedel-Crafts dealkylation, the backward reaction, proceeds via protonation of the electron-rich arene para to the electrofuge, or the future electrofuge. And then there are, this is in the gas phase, so maybe this is intramolecular, maybe this is intramolecular, I'm not so sure, but there are 1-2 shifts, and eventually the system can lose the carbenium ion. Whereas in the silicon case, protonation occurs in the ipso position, and then this is a low energy Wheeler intermediate because of the beta silicon effect. So the silicon atom will stabilize the positive charge. And then the silylium ion simply falls off because of the arene, because any Lewis base will mop up the silylium ion. So this is why the backward reaction is so facile. Now, we published a review, a mini review in Angewandte in 2017, summarizing our efforts to get such a reaction, such a Siler-Friedel-Crafts reaction to work and to go. And this did indeed work. We developed a few methods that, at least for electron-rich arenes, that enable such transformation. But I only share with you one approach that we've taken, because that has been really opening doors for us for the chemistry that I will talk about in the second half of my talk. So when E.J. Corey introduced silicon protective groups in the mid-90s to synthesis, most of these reagents, the Siler triflates and the Siler chlorides, were not commercial. So they had to make some of these reagents themselves. For instance, TIPS triflate can be easily prepared from triisopropyl silane by treatment with triflic acid. Now, this is an interesting reaction by itself. Excuse me. This is an interesting reaction by itself. because the acid is apparently able to protonate off the hydride, which is the leaving group. Mechanistically very intriguing. So this works nicely. When you run the very same reaction with an aryl group at the silicon atom, this has been done by Bassindale, a retired silicon chemist from the UK. So when Bassindale subjected this phenyl substitute hydrosilane to a reaction with triflic acid, that hydrogen atom stays in the silicon reagent, whereas there is dearylation. This is what you would expect, given what I've told you before, that the proto-dearylation is a facile process, and this is exactly what happens. So my postdoc at the time, Chinan Chen, he's now an independent professor in Dalian. So Chinan Chen repeated this reaction using the very same silane, deuterated or non-deuterated, and he used Brookhardt's acid, supposed to be also very strong acid. Now, Brookhardt's acid comes with 2 molecules of ether. It's an oxonium ion. So when treating this silane with Brookhardt's acid, there is DH or H2 being formed. This is a surprise. Or we can monitor the silicon atom. We get beautifully and very cleanly the ether stabilized Silylium ion. So this is the reversal of chemoselectivity. The triflic acid took out the phenyl group as expected, where Brookhardt's acid doesn't do that. This was a big surprise. We didn't have a real explanation for that, and we did publish this in JACS without explaining this switching chemoselectivity, because we made use of this method for the Silylium-Crafts reaction. So this was the purpose of the paper. But 2 years later, in Auner and Holthausen from Frankfurt, they published a paper, not even citing our works. They did not make a connection to our work, but we immediately made a connection to their work, because in a different context, they had looked into the protolysis of silanes activated by ether molecules. So the ether that comes with Brookhardt's acid coordinates, forms a weak Lewis pair with the silane. So with the silane here, you can see this here. This is now a trigonal bipyramid that shifts the HOMO of the system from the pi system to the silicon hydrogen sigma bond, which is now ready to be protonated, and hydride goes out. So hydride becomes the leaving group. So this explains the reverse in chemoselectivity. We then made use of this catalytic system for Silylium-Crafts chemistry, and believe it or not, protons are our enemy. So whenever you would run a column with silica gel on this silated indole, it would immediately lose the silane group by protodesylation. We now use the acid to get this reaction to work. This is quite remarkable, and electron-rich arenes can be silylated indeed with this in situ formed Silylium ion. The yields are okay-ish. The reaction is not about scope. Of course, the scope is heavily limited because of the acidic conditions with the Silylium ion, which is a very good Lewis acid. And it doesn't like oxygen donors, of course, because of the oxophilicity of the silicon. But for those systems you see here, electron-rich heteroarenes and aniline derivatives, it works quite well. And it's a surprising result because you would think that the protons will immediately destroy the product. So this paper, this accomplishment by Chinan was really an eye-opener for us. And so the decision we made is we need to get away from Brookhardt's acid. So Brookhardt's acid is, for our purposes, actually not so practical. Look, Brookhardt's acid comes with ether molecules, and you cannot get Brookhardt's acid ether-free, because once you try to get rid of the ether, the proton will borylate the fluorinated arene. So it decomposes the counter anion. So we made a big decision in the lab. We decided to look into Chris Reed's carborane acid. So Chris Reed's, I think, most remarkable accomplishment is that he developed these carborane-based acids. This is the world's strongest Bernstein acid with a super weakly coordinating counter anion. And so we invested the time and effort to make this counter anion, and we made the acid. The acid, however, is not so easy to get completely water-free, and water is no good for selenium ion chemistry. So we changed our mind and moved from the proton to the rhenium ion. This is protonated benzene. It's an rhenium ion. This is a Wheelan complex. I would have never thought that we can make this compound basically in gram quantities, put it into a vial, and store it in the glove box. Excuse me. So this acid is now available, and we have it in our glove box, so we can do chemistry with it. So the first thing that we tackled is, can we take this acid and either protonate off an aryl group or a hydride to form selenium ions? Because tertiary selenium ions had been long known by Lambert and by many others, including us. But there had been no examples of secondary, primary, or even the parent compound, no examples. So we decided to investigate this, and I should mention that the t-butyl group here at the silicon atom is not a strict requirement, but to obtain good NMR data and clean NMR, we need a t-butyl group, because without a t-butyl group, selenium ions undergo substituent scrambling with unreacted silanes. So we get mixtures of silanes with ligand scrambling. With a t-butyl group, we shut down this pathway. This has been investigated by Mookie Baik from KAIST together with us, and this and the mechanism for this has been reported in Chemical Science a few years back. Okay, so Qian, with her golden hands, she managed to make the secondary selenium ion either by protolysis, dehydrogenative protolysis, or by protodearylation. Here's the X-ray of the counter-anion stabilized secondary selenium ion. She did the very same thing with a primary system that also works beautifully. Well, I think at this stage, this would have been a very nice publication at decent level or at high level. And I was almost about to ask her to start the manuscript writing, but then she accomplished what I would have never thought is possible on planet Earth, I have to say. She managed to make SiH3+, the parent compound. We didn't start from monosilane. This is a nasty gas, but phenolsilane is easy to handle. So protodearylation gives SiH3+. So this is really remarkable because this is a species which is one of the strongest Lewis acids that is out there. Here's the molecular structure. It forms a linear oligomer, and it requires 2 counter-anions to stabilize the SiH3+, and it's now a trigonal bipyramid. In fact, the X-ray is exactly the same as the X-ray of the proton. So Chris Reed has an X-ray of the proton, basically. So this qualifies now the silicon, the SiH3+, as the fat hydrogen atom, a term that has been introduced by Ian Fleming many, many years ago. So in one paper, we described a tertiary, but also secondary, primary selenium ion, and also the parent compound, whereas for the carbenium ions, the primary system is still not fully characterized. Okay, so the team that accomplished this is shown here. Now, Henrik 5 years ago, me 5 years ago, Martin Kaub and his co-worker did the computations. Dr. Aaron is the crystallographer, and Qian, with her golden hands, she managed to crystallize these compounds repeatedly. She could do it on demand. Really, really amazing hands. And she's now professor in Nankai University. Okay, I will show you one more example, although it seems to get kind of boring now. But the difference here is now that we use hexamethyl disilane, and we don't protonate off hydrogen hydride or an aryl group. We can also protonate off alkyl groups. This is going to be important in a minute. So we can proto-dealkylate a silane, in this case hexamethyl disilane, that also works with other silanes, and we form methane in this case, and this silicon substitute selenium ion. So you might argue that this is another maybe important example of a selenium ion, a silicon silane substitute or silicon stabilized selenium ion. But frankly speaking, it just seems like an addition to our collection. However, these species can be relevant in catalysis, and I show you one example. So this example shows that we exactly use this selenium ion and react it with an unactivated alkene. That adds across the alkene to form a beta silicon stabilized carbenium ion that engages in an interaction with a silicon-silicon sigma bond to this transition state computed by Stefan Grimme. And we do form this species, which we try to make for years independently, because this is a methonium ion, pentacoordinate carbon atom, cation. Spectacular structure, but we couldn't get our hands on this compound. This immediately decides not to exist anymore. And we have an intermolecular displacement of the methyl group. Here's the methyl group with the CH bond by the arene to form an arene stabilized selenium ion. This selenium ion is thermodynamically accessible, and it wouldn't be Qian not to crystallize this molecule. So here's the molecular structure of this important intermediate. And this selenium ion, as the proton does, can now capture a methyl group from hexamethyl disilane to form the product and reactivate otherwise inert hexamethyl disilane. So what this shows you is that you can use these reactive intermediates to enable catalysis that's not even possible with a transition metal, because transition metal cannot oxidatively add to the silicon-silicon bond of hexamethyl disilane. There is an example, but this has not been applied to catalysis. The platinum, NHC platinum complex can do that. So I think there is importance or relevance to these reactive species. And I show you some scope, particularly the cyclic alkenes are quite nice, because you can see that the reaction is diastereospecific, so the mechanism determines the relative stereochemistry of the products. Okay, and now the shuffle begins. So all you've seen is pre-pandemic. So this was all accomplished before the pandemic hit. And then we couldn't continue with this chemistry because our lab was closed a couple of times for extended periods of time. And we had a postdoc joining this project, basically succeeding Dr. Qian Wu. So all the chemistry I show you now has been done single-handedly by this postdoc, who's now a professor in Nanjing. Henrik and I did write a perspective during the pandemic, and this injects, and this perspective summarizes our thoughts and what we plan to do. So it's not summarizing what we have done, but what we plan to do. So the idea was to develop a shuffle between the different reactive intermediates. You've seen that we can take an arenium ion and convert it into a silylium ion. You have also seen or guessed that you can convert the silylium ion as part of catalytic cycle into a carbenium ion. And maybe the carbenium ion can be used to regenerate a proton as part of a sacrificial Friedel-Crafts reaction, because the arenium ion is nothing but a Wieland complex. So by maybe proper design, these reactive intermediates can be orchestrated in such a way that we can take specific advantage of either one of the three. And I show you three reactions before I close my talk. Three applications, one dealing with the carbenium ion, one dealing with the silylium ion, and one dealing with a proton. But they all rely on this shuffle. First example. Friedel-Crafts methylation is accomplished under zeolite catalysis in the petrochemical industry. And so in excess of the arene is treated with methanol. So methanol is the methyl cation source. And this is, I think, in the gas phase, is put in quick contact with a zeolite catalyst at high temperature and high pressure. Contact should be short to avoid over-alkylation or over-methylation. So I show you now that we can use super electrophile catalysis to achieve the very same reaction under much milder conditions. To calibrate you a little bit, Meerwein salt, which is, I guess, this is what we teach, a very, very strong methylating agent. It's a methyl plus source. Meerwein salt cannot methylate benzene. However, when we protonate with Reed's acid and this counter anion with the rhenium ion, we can protonate methanol. This can actually methylate benzene. So this is a strong methylating reagent. When we put on a silylium ion, so you have all three choices in one oxonium ion, it also works. So what I show you now is the use of catalytic generated oxonium ions, let's say Meerwein salt type oxonium ions, and we make use of them in the methylation of arenes. And here are the results. So I guess benzene itself is not so interesting, but toluene is interesting because the xylenes are relevant products, and this works beautifully. Of course, there's no regiochemistry, but 100 degrees. What's more exciting is that we can even take chlorobenzene or dichlorobenzene or even the fluorinated derivatives to work. So the system is so potent that we can now do a methylation under rather mild conditions of totally unreactive arenes. And this, I think, shows that by design, one can now make use of these reactive intermediates in a catalytic process. Let me walk you through the catalysis real quick. It has a self-healing character. The methanol gets activated by the Silylium ion. The Silylium ion forms this oxonium ion. The oxonium ion can protonate the sacrificial arrow substituted silane to form a wheeler intermediate and the silylated methanol. The silylated wheeler intermediate will of course lose the Silylium ion. Protodesylylation happens. We form the bisilylated oxonium ion, where the leaving group is of course the disiloxane, which is a pretty poor donor. So this really likes to depart, and the methyl cation will then engage in a Friedel-Crafts methylation of the arene, forming a wheeler intermediate, which itself is of course a strong acid, which will protonate of a Silylium ion, and so on. And so we stay in this catalytic cycle. Okay, so we can do the very same thing, not using an alcohol or ether. We can also use alkyl halides and do now under mild conditions Friedel-Crafts alkylation, Silylium ion promoted Friedel-Crafts alkylation using alkyl halides. They have a number of advantages, particularly no defunctionalization of delicate functional groups. But I like to skip this in the interest of time and show you the next application. Now, the next application is particularly intriguing because it enables a reaction that I would not have thought being possible. We again start with an alkyl halide. We treat this with a Silylium ion, forming a halonium ion, and the halonium ion can, of course, either release a Silylium ion, this is the backward reaction, or it can release a carbenium ion. The carbenium ion can react with benzene, for instance, in a Friedel-Crafts alkylation, forming this wheeler intermediate, and release the halosilane or the silyl halide. And this can be the desired product, as you will see in a minute. So we form in situ the actual catalyst of the system, which is this arenium ion, the product of this initial Friedel-Crafts alkylation. That is a strong acid. They can protonate off an alkyl group of the silane. If this is a methyl group, it's methane being formed. We form the desired Silylium ion from the tetraalkyl silane. This can form a halonium ion, and the halonium ion then can release again the carbenium ion in a sacrificial Friedel-Crafts alkylation, releasing the silyl halide and reforming the catalyst. So it's a coupled process of a proto-dealkylation and then a chlorination, and the overall process is a chloro or halo dealkylation of totally inert, fully alkylated silanes. I'd like to briefly explain the mechanism to you because that is, I think, not that obvious. This was done by Stefan Grimme or computed by Stefan Grimme. I would have always thought that when we have this acid, it would protonate the carbon sigma bond, the silicon carbon sigma bond by side-on protonation because the electron density should be between the silicon and the carbon atom. However, the electron density of that bond is high enough on the backside, so we indeed have backside protonation of the silicon carbon bond, and this releases methane, benzene, of course, and the selenium ion. And you can imagine that this backside protonation is very sensitive towards steric hindrance. So in the reaction that we develop at room temperature, we take a tetraalkyl substitute silane. We use, for convenience, not methyl chloride because that's a gas. We use dichloroethane. And when we treat this with a tiny bit of selenium ion, we can convert the tetraalkyl silane into a silyl halide. The reaction is very chemoselective. We can even distinguish for the reasons I've given before, methyl and ethyl, two primary alkyl groups. It's not perfect, but still pretty impressive to distinguish between those groups. Generally speaking, the chemoselectivity is outstanding, so we can easily distinguish. I will not go through all these examples, but we can distinguish, I guess I can summarize here, primary from secondary, secondary from tertiary, and also primary from tertiary, of course, and we can even distinguish smaller ethyl, for instance, from longer aliphatic chains such as N-butyl. And as a demonstration of this, this is a fun reaction sequence. We can convert tetramethylsilane by halo dealkylation, chloro dealkylation, substitution, N-butyl comes in. Again, chemoselective halo dealkylation, then substitution with N-propyl magnesium bromide brings in the N-propyl group. Again, chemoselective chloro dealkylation, and then bringing in an ethyl group, we can transform the homoleptic silicon compound into a silicon compound heteroleptic, so to say, with 4 different substituents. And there are other applications to it. Well, the importance of this chemistry, here is the summary of the answer to the riddle, is that when we mix those compounds, we in fact get toluene as byproduct, but that's not an issue, methane as a gas, and we get TMS chloride from tetramethylsilane. And the importance and beauty of this is that we can take waste material from the Müller-Rochow process and convert it back under very mild conditions into a useful product. And I can also already say, we just published this a week ago, that we can even go directly from tetramethylsilane to dimethyl dichlorosilane. We simply need to increase the temperature, and so we can even make the dichlorosilane. So the dichloro and the monochlorosilane, these are important, the important products of the Müller-Rochow process. So this is how we convert back or can upgrade or upcycle the tetramethylsilane again. So to close, I only have one more little project to share with you. I've shown you now chemistry with a Silylium ion, or where the silicon is in the center of attention. One with a carbenium ion, the methylation of the arenes, and now I show you where the protons are relevant. Now, it's long known that electron-rich arenes can be deuterated by HD exchange under acidic conditions. This is how you make C6D6, benzene, and deuterated sulfuric acid. And it was J. Siegel, for instance, to understand that you can also start with C6D6 and have a transfer deuteration under acidic conditions. And his former student, Duttweiler, did the same thing with a different acid, so PFBS, so it's a hydrotriflic acid derivative. But J. Siegel used the mesothelium ion, and this is not a superacid. And also this is not a superacid. When we use the rhenium ion, the benzenium ion, it's a whole different story. We take a very unreactive arene, dichlorobenzene, and only you can see the data for all the other common acids, or less common but seemingly reactive acids. That's not the case. They are not good enough. You need the rhenium ion, the benzenium ion, or the Silylium ion to promote this HD exchange. Because I go back one slide, it's remarkable to see that the difference in pKa units between the mesothelium ion, so 3 methyl groups, and the benzenium ion, I think is 4 or 5 pKa units. This is -18, this is -13 pKa, if I remember correctly. So this works beautifully. We can finally make all these deuterated halogenated arenes, and the importance is for us that dichlorobenzene is the perfect NMR solvent, and we use massive amounts of deuterated dichlorobenzene. It costs me several thousand euros a year. Dichlorobenzene is a fantastic solvent because it is more polar than dichloromethane, and it is robust. Whereas strong Lewis acids decompose dichloromethane, dichlorobenzene stays intact, and also difluorobenzene. So we have to buy this expensive NMR solvent. I don't know how the company makes that NMR solvent. I don't even know how they make the deuterated difluorobenzene, which is an equally attractive NMR solvent. So with this method, we can now really get our hands on these deuterated, halogenated, electron-deficient arenes, and it works also for the other halogenated systems. Maybe I mentioned the penta substitute system, which doesn't work, but this we can deprotonate and then add a D+ source. So there are other ways of making it. Okay, finally, Tau did this on larger scale. We only use 1.1 mole% of the uranium ion as catalyst. We need 2 runs for full detuturation, and then one can relatively easily separate the dichlorobenzene from benzene. Difference in boiling point is sufficient. This brings me to an end of my talk. This is my final chemical slide. You've seen that slide before. This is what the shuffle is all about. We think that we can design systems, and we have demonstrated this already for 3-4 systems. We can shuffle between those reactive intermediates and make use of them in a targeted way. And I hope that this approach will bring about further discoveries in transition metal-free catalysis. I would like to close with thanking my group. I've mentioned the people who have been responsible for the chemistry I've been talking about today. I think no one is in the group anymore except for Henrik. The current group members are working on very different projects. Usually I only have 1 or 2 people working on this delicate Silylium ion chemistry. I thank my whole group for their efforts and for their hard work they put into our research program. I'd like to thank the funding agencies for constant support. And of course, I'd like to thank Larry for writing the biography. I thank everybody for coming and listening. And I thank again Pilar for the nice introduction, Anne and Wiley for the organization of the event. And there are no questions, so I hand back to Pilar to introduce Dave. Thank you.
Yeah, thank you very much, Martin, for this really nice overview. Yeah, we learned a little bit about the Lives in Chemistry book series, then how you got into silicon chemistry, and then some applications of your Silylium ion catalysis that you've published over the last few years. And as you said, Martin, there are no questions, but of course, people that are interested in learning more, they can read your fantastic publications and maybe even reach out to you. If there are.
Sorry that my voice was not so good, but I had already 4 years of teaching already today, so I've been shouting at the audience for several hours today. So
no problem. I think it was perfectly fine. Yeah. Okay, I think then we will move on to the next speaker of today's event, and that's Dave MacMillan. I will briefly introduce him now. So Dave received his undergraduate degree in chemistry from the University of Glasgow. In 1990, he then moved to the United States and began his doctoral studies, with no other than Larry Overman at the University of California in Irvine. In 1996, he then took on a postdoctoral position with Professor Dave Evans at Harvard University. He began his independent career in 1998 at the University of California, Berkeley, before moving to Caltech in 2000 as chair of organic chemistry. In 2006, he then moved to the Department of Chemistry at Princeton University. Here he served as the department chair from 2010 to 2015, and currently he's the James McDonald Distinguished University Professor of Chemistry at Princeton University. His research interests center around finding new concepts in catalysis, exemplified by many transformations that he has developed in the fields of organic catalysis mainly and photoredox catalysis, and then also their applications in the synthesis of natural products and pharmaceuticals. He's been well recognized throughout his career with many awards. He's won, for example, the Cope Award, the Roy Noyori Prize. He's an elected fellow of the Royal Society of Chemistry, and of course, most prominently in 2021, he won the Nobel Prize for the development of asymmetric organocatalysis that he shares together with Ben List. Dave, we're really happy to have you here today, and I would now like to pass on to you, and we're really looking forward to your talk entitled Larry Overman, an amazing chemist, mentor, and role model. And we're excited about what you want to share with us today. Thank you.
Thank you, Anne, for that very generous introduction. Honestly, it's an incredible pleasure and privilege to be part of this, along with Martin, to be here to honor Larry and to obviously celebrate the publishing of this fantastic autobiography. I will point out, I actually have a copy of this. I actually managed to get a hold of one, and I thoroughly recommend it. It's a great read, and there's lots of parts in there which I did not know about and found absolutely fascinating along the way. So, you know, I just want to congratulate Larry for that. I have a whole range of things I want to say about Larry, but I'm not going to say them now. I'm going to wait till the end of my talk. That way, to try and enforce people to stick around and actually listen to my talk. So I'm going to do it that way. So let me just kick off with my talk first, and then I'll leave the last 10 to 15 minutes or so to chat a little bit about Larry. Okay, and I hope you can all see this. So yeah, Larry Overman, I think everyone knows this, an amazing chemist, mentor, and role model. But for my part of this, I was going to talk about, you know, some ongoing things that are happening in my lab right now. I also, in trying to decide what I wanted to talk about, I actually picked out two relatively new components of my lab's research that actually I know that Larry has told me he's enjoyed hearing about. So I thought I'd sort of focus it on these two projects that he's at least told me he likes them. So I thought I'd sort of try and focus it that way. To give a little bit of background, one of the things that my lab works a lot about, or thinks a lot about, is how to take a lot of the knowledge or information that's come from physical and organic chemists about using visible light that they have been sort of working on and thinking about trying to harness solar energy, or trying to basically harness sunlight to power the planet, and how using that knowledge they've been able to sort of translate it to catalysis. And we became really interested in taking that knowledge and transferring it into the world of organic chemistry. In particular, this area called photoredox catalysis, which allows you to make nice videos like the ones which are actually shown here. What's interesting for me in this world of photoredox is probably over the last couple of years now, many people have asked me to sort of give reflections on why we became interested in certain areas of our research. And one of those has been photoredox catalysis, why we're interested in doing it. But also a question about why do I think photoredox sort of took off and became the area that has become for our community, which is a really interesting question and not necessarily an easy one to answer. But in retrospect, the way that I think about it is one of the things which allows photoredox to become broadly effectively employed or adopted is the idea that allows you to take native functional groups or molecules that are broadly available in structural diversity on our planet right now and commercially accessible, but also molecules which are reasonably stable. They're low energy molecules. Some people would call them chemical feedstocks. And through being able to channel photons, and these photons of, say, blue photons, which are really interesting because, well, you could shine a blue photon on your hand all day long, wouldn't do anything at your hand, but when it's absorbed by these catalysts, they become the equivalent of 32,000 degrees Celsius, which is really interesting because you now have a molecule which is effectively a completely different energy scale from every other molecule which is in that vessel. It has to offload that energy in some way, and the way that it does it is either through energy transfer or electron transfer. But one of the key aspects of this, there's such a driving force to do it, and it's able to therefore take these molecules that are relatively stable and low energy species and make them into these high energy radicals. And you're making these high energy radicals from very stable materials instead of having that energy built into the start material, which I would argue, well, there's been tremendous advances in radical chemistry. A lot of it was using high energy starting materials to generate radicals. This is not doing that. This is taking broadly available materials to effectively generate radicals. With these radicals in hand, you can now start to think about lots of new chemical reactions, and here are just some of them which are shown here. And I think the critical component of this has been the adoption by pharmaceutical companies, agrochemical companies, fine chemical companies. And again, I think a lot of that goes back to the accessibility of unique start materials for structural diversity in the molecules that they're trying to access. Now, a subfield within photoredox catalysis is one that's called Metallophotoredox catalysis. And as cumbersome as that name sounds, it's actually a pretty simple idea. It's where you take photocatalysis, so the key elementary steps of photocatalysis, and you merge it with known transition metal catalysis things, such as oxidative addition, transmetallation, reductive elimination, with the goal towards bringing these two components together to hopefully allow new catalytic ideas or concepts, new bond-forming reactions, so on and so forth. Now, our initial interest in this was a very simple idea, which is one shown here. And it was the idea, was known that if you take nickel 0 or nickel 1 with an aromatic bromide, we know that that will do oxidative addition to generate a nickel 2 aryl species. But a few years ago, Greg Fu and others beautifully established the idea that you can indeed generate radicals, and radicals will add to these nickel 2 species, become nickel 3, and do reductive elimination. Now, our interest in this became, as I just mentioned a few moments ago, we've been saying we can use photoredox to generate radicals from many different start materials. And as such, this starts to open up the possibility now of new molecules you can use for cross-coupling. Anything effectively you can make a radical from. So for example, we thought maybe we could take abundant biomass, such as amino acids, such as proline shown here. Could you expose it to a photocatalyst with a blue photon? And this excited state should be able to perform electron transfer. Decarboxylation should generate the radical here. It undergoes addition to nickel 2, and then reductive elimination would effectively allow a new bond forming reaction from an abundant biomass. So we set out to test this, and it worked. And we published this back in 2014 in a collaboration with Abby Doyle's group. And to be honest with you, at this moment, we realized we thought this was an interesting concept. We decided we wanted to exploit it to its fullest extent, and we certainly took it to the bank. We worked on this in a lot of different directions. And I would argue many other people with similar ideas were doing the same thing in electrochemistry, as well as reducing metal chemistry as well, which really led to a significant, I would say, employment of nickel catalysis broadly for a whole range of different bond forming processes. Now, from my own perspective, I've been very lucky over the last 2 decades in that I've been asked to consult for a range of pharmaceutical companies. And when I would visit these companies, I would always ask them or take a survey of which photoredox reactions they were actually using. And I would talk to them about this. They would say, yeah, it turns out that the reactions on the right-hand side, these are ones that we use extensively. These are called cross-electrophile couplings because you're using 2 different electrophiles to couple them, which was great to hear. But at the same time, when I would ask them about the first reaction we developed, this decarboxylative coupling, they say, yeah, we don't really use it that much. And the reason is it's not really general. It only works about 20% of the time, which is obviously pretty disappointing because this was the first transformation we'd actually developed with nickel. Now, you may ask yourself, well, why would you care? If the cross-electrophile coupling is general, why do you care that the other one is not general? You've got certainly ways in which people can employ this idea. Why do you care about this reaction on the left-hand side? Well, for us, there was a whole range of reasons why we cared about this. The first one was to think about the diversity of start materials that are available to these scientists that we're hoping are actually going to use these transformations. So what I'm showing here is the number of commercial alkyl sources that you can find in any given commercial sourcing book. And you can see the relative amounts of these alkyl halides. And I'm going to contrast that against the number of cross-coupling reactions that are actually performed with them. And you can see that the alkyl bromide really outpaces all the other different halides. But to our mind, something that was even more interesting was there's even far greater availability of carboxylic acids. And yet, again, there's very few cross-coupling reactions in relation to the alkyl bromide system. So for this reason, we thought it would be important to try and develop a general version of using carboxylic acids for cross-coupling. So that was the goal. Could we actually develop a general version of this? Now, you may ask yourself, generality, is that important? And I would argue that along with things like new reactions, new reactivity, selectivity, generality is one of the most important components of any given chemical reaction, especially if it's going to achieve adoption. If people are actually going to use it, it has to be reasonably general for people to actually do this. I would also argue the way that we normally think about how you get to a general reaction is using this schematic, which I've shown here. We typically, to achieve generality, we will look at a chemical reaction. We'll try and gain some mechanistic insight that will take it into a new reaction development and hopefully lead to an improved reaction. And at this right-hand side, we then go back to the beginning, we increase or add additional mechanistic insight, and we keep going through this iterative cycle until hopefully we'd reach what we would call a general reaction. Now, I would argue some of the most powerful reactions in the world have achieved generality. And here are just some of them shown here. Without question, olefin metathesis, extraordinarily general, extraordinarily powerful. CN cross-coupling, the Buchwald-Hartwig reaction, extraordinarily powerful because it is so general. However, if you look at the Buchwald-Hartwig cross-coupling, one of the things which I always like to point out, if you look at where Steve Buchwald began on this to where he ended up, there were significant developments in catalyst or ligand design along the way. And one thing you have to concede is this is extraordinarily beautiful work, but it took time. It took years to decades to actually for this to be accomplished. And for me, this idea that we're going to have to take decades to develop a general decarboxylative coupling didn't feel this would be a reasonable way to look at solving this reaction. So we started to think, could we actually develop an accelerated approach to reaction generality? So what does that actually mean? Well, instead of using this traditional approach, which I've shown up here, which I would call the chemist's approach to generality, we started to ask, could we actually use a biologist approach to generality? Now, what on earth does that mean? Well, it was really, can you use like a phenotypic, unbiased approach to trying to achieve generality? So the idea here is that we're going to look for the outcome first. So we're going to perform basically high throughput additive evaluations. We're going to hope that we can quickly have a hit identification that will quickly lead to a general reaction. But this would be a general reaction or an outcome that we want, but we've actually no idea how we accomplished it. It would only be we're achieving the generality first. So at the end of all of this, we would then want to study why the reaction became general via mechanistic insight. So we would hope, all the mechanistic insight at the end of the process instead of at the beginning, more of the way that a biologist approaches trying to understand a biological mechanism. Okay, now to do this, we were incredibly fortunate to get to collaborate with some fantastic scientists at Merck. This is Spencer Dreyer and Shane Kriska, in combination with two wonderful graduate students, Jacob Kotsky and Nico Komar, both from my group. And the first thing we started to think about is how we're actually going to perform this high throughput evaluation. And you realize that you can't study a single chemical reaction, or at least one overall transformation, because even if you can make it successful, how do you know that it's actually general? You don't. So as such, we recognize what we would have to do is simultaneously study a whole range of classes of both aryl bromides and carboxylic acids, the two different coupling partners involved, which is obviously going to involve a very large number of transformations that we'd have to perform simultaneously. Now, fortunately, Merck has an absolutely fantastic setup to be able to do high throughput evaluation of photoredox reactions. This is a system that they perform on nanoscale reactors. They can perform more than 10,000 reactions per day. They can actually perform, I think, more than 30,000 reactions per day, and also achieve a very large number of evaluations or analysis of those chemical reactions. So along with Merck, we actually performed this. And what I'm going to show you here is basically the outcomes. If you see the bottom here, we're actually using 721 additives. We're adding 721 additives to see the impact. And the average yield is the one that's shown here in the dotted line. And you can see for the most part, most additives don't really do anything. A number of them are actually quite detrimental. As you can see, it actually pushes the yield lower. However, we started to see that a number of additives actually gave a significant improvement in yield, up to a 4.5-fold improvement in yield across a whole range of substrates. And more interestingly, when we actually looked at what those additives were, we could immediately see they're very much related to each other. They're 5-membered imides. So based on this, we sort of honed in and said, all right, let's perform a more focused series of experiments now with 64 different imides. And when we did this, we actually found out some interesting SAR. The first part was that the nitrogen had to be unsubstituted. It had to be an NH bond. It did have to be a 5-membered imide, but it could be a 5-membered imide which is attached to another ring, aliphatic or aromatic, didn't really matter. And as it turned out, the best additive was actually phthalimide, which was wonderful. I mean, because phthalimide is so inexpensive. Now, at this stage, you have to try and come up with ways of trying to prove to people that this really is general. One way we were able to approach that was to actually take what's known as the Merck Chemistry Informer Library. This is 18 molecules that Merck have found are molecules which are not particularly great at most cross-coupling reactions. So when you utilize these, they don't often work. And anytime a new reaction is published, they test it against these 18 molecules and they give it a score. So we did that. We actually took 18 of them, although there's only 8 shown here. First of all, we tested them without phthalimide, and as you can see, most of these transformations are not particularly successful. One of them is, but for the most part, they're not very good. However, when you add phthalimide to them, you now see a significant improvement in yield, to an extent that this would now allow any given medchem program to effectively go forward based upon these yields. For publication, the other way we thought we could do this was actually to show the overall change. So this is the delta for all these different substrate classes. First of all, for the carboxylic acid substrate class, you can see for almost all of those, you see a significant improvement in overall efficiency by adding phthalimide to them. The tertiary carboxylic acid, it's not so great, but we'll come back and talk about that in a few more slides. But effectively, the same thing is true for the aromatics or the heteroaromatics. But again, you can see this overall delta, a significant improvement simply by adding phthalimide to this transformation. So this is great. We've been able to effectively achieve what we now believe is a reasonably general reaction. But again, at this stage, we've actually no idea why this is working. So what is actually really going on? Can we now try and achieve some mechanistic insight? So at this stage, I thought basically what was probably happening is we're adding phthalimide and it's fixing one component of the mechanism and it's switching on all these reactions. And it turns out that was completely wrong. That was not the right way to think about this. And indeed, the more we sort of dug into this, we actually found there's at least 6 different reasons. I'm showing you 5 of them here. There's 6 different reasons why phthalimide is able to effectively rescue this transformation. And if you think about it, that makes sense because we performed a phenotypic screen to try and get success. So we achieve success first. So the additive that's achieving success must be solving a range of different problems. And that's exactly what is actually going on. So I'm not going to go through all the different aspects at which it overcomes, but I'll just show you 2 quick ones, which I think are interesting. If you remember, I told you that nickel does oxidative addition into the aromatic bromide to generate the nickel aryl species. And when you don't have phthalimide, the carboxylate substrate actually takes up this 4th coordination site. As it happens, that oxidative addition adduct is really unstable. It's so unstable, it will readily protonate if a radical is not generated fast enough to trap the nickel. In contrast, when you run the reaction with phthalimide, phthalimide actually displaces this carboxylate and actually now forms a nickel species which is extremely stable. It's stable to the point that you can actually grow crystal structures of it. And indeed, if you expose this molecule to a radical generated by almost any means, it's competent for bond formation. So that was great. That was one nice feature we observed was actually taking place. The second one is if you actually look at this transformation, this is a prototypical transformation, the way we would run this without phthalimide, and you can see the reaction stalling at low yield after about 2 hours. And what is actually happening here is you're actually generating nickel-1 species that dimerize. They form these head-to-tail dimers, which are very, very stable. They're so stable that they won't even react with an aromatic iodide. They won't do oxidative addition. But if you go back to the same reaction and you now add phthalimide to it, it reignites it. It kicks back in again. And what's happening here is effectively the phthalimide is going in and it's breaking up these dimers back to the monomers, which are then catalytically competent all over again, which has been another nice feature of this overall transformation. So as such, we've been really excited about this because we've taken a reaction on the left that was previously just not working, and we've now made it suitably general. And it's suitably general that both now Merck and Pfizer are now employing it again in their high throughput screens for generating new molecules, which has been really fantastic to see and obviously very satisfying. At this stage, we started to think, okay, that's great that we've achieved what we think is generality here. Is there other couplings we would hope to develop that could be equally general? And to think about that, I'm going to take you back to this bar graph. And I pointed out to you it was important for us to think about the diversity or accessibility of these starting materials. And you can see there's obviously a space at the bottom of this bar graph. There's something missing here that I'm not showing you. And what I'm not showing you is actually alcohols. And this was really fascinating to us because you can see here, alcohols are just so broadly available from commercial sources in extremely diverse structural formats. But you think about deoxygenative carbon-carbon bond forming reactions, there's very few. There are very few of these that have actually been accomplished. So with this in mind, we started to think, wouldn't it be great if you could actually do that? If you could focus on using alcohols to do this. One way you could ask yourself, why would this be interesting? For example, intuitively to a chemist, imagine if you were to take a molecule such as Taxol, and if you could simply stitch in an aromatic ring at that position. I think we would all think that would be pretty interesting. Okay, so how are we going to do this? Well, the concept was the following. Could we possibly develop a new reagent, a reagent that were for basically almost any alcohol with less than 5 minutes activation would attach to an alcohol, and through photoredox or other electron transfer type activations, be able to convert that alcohol to a carbon radical species. Now, we thought about this for a long time, didn't really go anywhere until this really phenomenal postdoc in my group, Jie Dong. He's now a professor back in SUSTEC in Shenzhen, back in China. And Jie came up with this really phenomenal idea, which was, why don't we use NHCs? And the idea here was that these NHCs should be able to react with almost any alcohol very rapidly. Now, I'll sort of give a little bit of the story away, tell you these are now produced on a very large scale. They have really interesting tunable Irvine electronics that allow you to do some other interesting things with them. But at the outset, the original idea here was once it undergoes addition to the alcohol, if you then remove an electron, you should generate a radical, you should undergo beta scission to generate a stable byproduct, the carbon radical species that should now interface with nickel-2 and allow the cross-coupled product to be formed. Now, this actually worked, and we published this back in 2021. There's many examples that are actually in this paper. I'm not going to go through them all. It's a little bit like reading the phone book, but I thought I'd just show you a few examples to sort of give you a flavor of what you can actually do here. On the left-hand side, this case where you have trifluoroethanol, to generate a radical next to a CF3 group is a really high energy species and very difficult to do. So we thought that would be problematic. And the one next to it, you've got a 1,2 diol, and there's a case here, can you activate the primary alcohol in the presence of the secondary? And it turns out you can do both of those successfully. On the right-hand side, you can see this is the spirocyclic bicyclic. This is a bridge bicyclic. On the right-hand side, you've got a bromide, but you've also got an alcohol. But we want to do the chemistry at the alcohol position, not the bromide. And indeed, you can do that. I mentioned a few slides back with problems with the tertiary decarboxylation. With alcohols, we can do those just fine. They work great. And for hexoses and nucleotides, both at the anomeric position, but also in the backbone of these scaffolds, again, you can stitch in these aromatics. One feature of this, which we absolutely did not see coming, it was completely serendipitous, was when we actually attempted this reaction using cyclic or acyclic 1,2 diols. We actually thought this would lead to just a statistical combination of different arylation products, but that's not what happened. What effectively happened is it successfully undergoes a mono addition with the NHC, which allows a mono arylation. What's nice about this is you can take the products directly and then put them into a completely different arylation reaction, effectively using those two alcohols to make drug-like molecules in a very rapid process, 2 chemical steps, while retaining stereo control around these different systems by diastereo selectivity. And just to sort of point out, and this is going back to this original concept slide of using Taxol, this is a protected form of Taxol, and we can indeed stitch in an aromatic. Now, this is 25% yield, which is not the greatest yield in the world, but again, that would allow a medicinal chemistry program to go forward. And given the complexity of this system and the difficulty of doing that next to a neopentyl carbon, we actually thought this was something that was worth publishing. Okay, so at this stage, what I'm going to do is take you into the second part of my talk. I'm going to talk about this chemistry we've been developing, which we call basically the employment of SH2 mechanism for a new cross-coupling reaction. So to set this up, one of the things I always enjoy sort of talking about has been the evolution of medicinal chemistry in the pharmaceutical industry over the last 20 years. It's been really interesting to see that while biological targets have changed, you could also make an argument that the molecules that medicinal chemists are making are also changing. And they're changing because they're becoming much more sp3 carbon rich. This has come about because of an analysis, or it's almost like a Moneyball analysis of understanding that molecules that are more likely to be successful through a whole program all the way through the clinic are more likely to have more sp3 carbon content. And that's led to an evolution of more of those types of carbons being introduced into more drug development candidates. Now, from my perspective, I was literally sitting in my office one day thinking about, well, wouldn't it be great if you could actually come up with a new way of joining sp3 carbons with other sp3 carbons in a heterocarbon selective bond forming process. And I told you at the beginning of my talk that we know that photoredox is great at generating radicals. So the idea was, what if you could generate, say, a primary radical in the presence of a tertiary radical? Shouldn't they undergo bond formation? That should be a barrierless process. And should it form this cross-selective product? Now, many of you will immediately see the fatal flaw in this idea, and that is, well, if these radicals can react with each other, they can react with themselves, they can do other things too, why would it be selective for this basically heteroselective process? Well, unperturbed by this, I managed to convince a postdoc to try it. His name was Wei Lu. He came back and he told me, yeah, it was a terrible idea. It was a complete mess. But he then said he'd been thinking about the overall idea, and he'd sort of come up with an alternative way of thinking about this. And he pointed out the way that nature has kind of solved this problem. And what nature has done is it actually uses this catalyst called cobalamin in biochemical systems, where you generate a radical, and the radical will actually undergo addition to methyl to do a methylation. Now, this is an SH2 mechanism, and for those of you who don't know what SH2 was, which would have included me 5 years ago, SH2 is simply the radical equivalent of an SN2, where a radical undergoes addition to a carbon, breaks the bond, and the leaving group itself is a carbon. Now, in this case, cobalt is a leaving group, and it's that change in the oxidation state of cobalt which makes it a radical leaving group, and they're really fantastic at being able to do this. Now, SH2 has some really great quotes. This is one from Michael Johnson that I won't read out to you, but you can sort of read it for yourself. I really love this quote. But we started to think, can we use SH2 as a design principle for achieving basically carbon-carbon bond formation between these sp3 carbons? So how would this work? Well, the idea behind this is, imagine you have a primary radical and you generate a tertiary radical. We believe that that primary radical should form a bond to the metal center. We believe this, first and foremost, because it should form a relatively strong bond. Now, the second part of this, we believe that the tertiary radical should now be able to undergo addition to that, an SH2 reaction, because it's a very nucleophilic radical to give you the cross-selective product. Okay, that's fine, but why won't it do homodimerization? Well, we believe that the primary radical should not add because it's going to be far less nucleophilic than the tertiary radical that's also available to it. So we think that would preclude primary dimerization. What about tertiary dimerization? Well, first and foremost, we didn't think the tertiary radical is likely to undergo addition to the metal because that should actually have an extraordinarily weak bond. If you actually computationally measure this, in many cases, this would be a negative BDE. But even if it did form, it would be a tetrahedral carbon, which would effectively preclude the second addition. This is no longer a barrierless addition. And as such, the only thing that would be left over or available would be the primary to react with the tertiary, give it this cross-selective product. Now, we set out to do this. This was a fantastic collaboration between my lab, which was Wei, who I just mentioned, and Marissa, a wonderful graduate student, Colin, a superb postdoc in my group, and Jesus Alcazar, who is a great collaborator from Janssen over in Toledo in Spain. And the idea here was we were going to perform a redox process. We're going to do reduction to generate decarboxylation radical. And through an oxidative process, we're going to remove or abstract this bromide, simultaneously generating these two radicals, which we hope will now undergo this selective cross-coupling through this SH2 mechanism. Now, we set out to do this, and again, I'm not going to go through all the scope of this. I've drawn this as an acid. These are actually not acids. I'm just trying to reduce some space considerations here. These are all redox active esters. But when you perform this chemistry now in the presence of an iron heme catalyst, this beautifully does this cross-selective radical-radical type coupling with very good levels of efficiency. And we're able to publish this back in 2021. But the key feature of this was it's effectively sorted out the two different radicals to ensure that they actually react with each other. At the end of this, it sort of raised two sort of major questions for me. The first one was, is it possible to take this radical sorting idea and make it in a general system? Is this a really generalizable concept? You can take basically a primary with a secondary radical or a primary with a tertiary radical, and through this mechanism, they will always select for cross-selectivity for new bond-forming reactions. That was the first question that we had. The second question was, do you have to use these iron heme systems? Would it work with other metals? And one of the things that we've now found that beyond the original 4, which are actually known in the literature, there's actually many other metals that are actually capable of actually doing SH2 chemistry, which is something we're very excited about because that opens the door to a range of other types of transformations. Okay, so what other things can you actually do? Well, one of the first things we decided to do was to take basically these pincer ligands with nickel. This was work of both Artem and Lorenzo, who are in my group, and actually now take 2 different carboxylic acids. And the hope here is that one of the carboxylic acids will be a primary carbon, the other carboxylic acid will be secondary or tertiary, and we're going to hope to decarboxylate both of them but through this mechanism, selectively cross-couple them with each other. To demonstrate how this would work, in this first case, where if you focus on the pink spot or the pink ball, these are the ones that we're going to decarboxylate, and we're going to expose it to vinegar, to acetic acid, to generate methyl radical. So we're hoping that a methyl radical will replace each of these carboxylic acids, and when we do that, that actually works quite well. It's not restricted just to acetic acid. You can do it with a whole range of different primary systems, and when you do so, you can nicely cross-couple those. In terms of the range of things that you can actually do here, this is just to demonstrate you can take drug-like molecules, take natural products, things which actually have very delicate functional groups such as aptasutinate, and indeed in these cases, again, you can actually do this cross-selective type radical sorting reaction. Okay, so at this stage, we're very excited about this mechanism. I'm not going to go through all the details of it, but we've now published, I think, 9 different papers on the SH2 system. You're now seeing other groups beginning to do SH2 chemistry and cross-coupling reactions, which is wonderful, and we're very excited that lots of other people are getting involved with doing this. This is exactly what we would like to see, is lots of different people really try and come up with the various ways you can exploit this mechanism. But for me, it sort of brought up this interesting concept about this whole business about just being able to think about simply taking a primary radical and a tertiary radical, or a primary radical and a secondary radical. And what does that mean for example, for retrosynthetic analysis? So indeed, look at the molecule which I'm showing here, and if you think about how am I actually going to form it, you can say, well, I should be able to form it from these 2 different radicals. But the other part that I like about this is you start to realize that this is effectively, I would call, a functional group agnostic transformation. Because as I told you at the beginning of my talk, we think with photoredox, you can make radicals from almost any functional group now. So as long as you take these any 2 functional groups that will form a radical, you should be able to do this overall transformation. So then that begs the question, well, if that's true, what 2 functional groups should you use? And the one that we became excited about was the idea, could you do this with 2 different alcohols? Could you literally take 2 different alcohols, have them both deoxygenate and cross-couple with each other? Now, I'm making this sound like this was a relatively recent idea, or at least the overriding concept behind it, but it's not. This is actually something my group has been trying to do for 17 years. At this point, we've actually had multiple group meetings on this over more than a decade, about trying to think about how to solve this problem. So why were we so interested in this? Well, if I take you back to another one of these sort of bar graphs showing the commercial availability of molecules, this is again going back to this idea of diverse structural formats. And these are the different types of functional groups that are available. Now, if I represent each of these numbers as a simple line, and if I say to you, well, imagine we're going to do a cross-electrophile coupling between 2 different alkyl bromides, the molecular space that you can actually generate there would be represented by this square, which is shown there. If I think about taking, for example, organometallics and cross-coupling it with any of these 3 different halides shown at the bottom, this would be the molecular space that you can potentially access. However, if you think about alcohols, and now the molecular space you can access through doing alcohol-alcohol cross-coupling, you can see it's enormous. And for us, this effectively gave us a strong impetus to think about, could we actually solve this problem? So how would this work? Why did we think we had a way of thinking about achieving this? Well, the notion here was take any 2 alcohols, put them in the same reaction vessel with each other, simply add an NHC. These NHCs should undergo addition. They should then be able to, under photoredox conditions, generate a radical, undergo beta scission. After they undergo beta scission, you generate these 2 different radicals. And now we hope that with an SH2 catalyst involved, that only the primary one will be able to add to the metal, but then only the secondary one will be able to do the SH2 onto the primary metal bond in the first place, effectively allowing you to take 2 different alcohols and do cross-coupling with them. Now, again, this was a really wonderful collaboration with Janssen, again, with Jesus, but now in this case with 6 folks in my group, Jerry, Nick, Jay, James, Colin, and Robert. This is some work that recently came out. It was just published a few months ago. And in terms of what you can actually do here, there's a whole range of things that you can do, and I just want to sort of take a few moments to walk you through them. First of all, in these cases, it was the idea, can you actually take all of these secondary alcohols with methanol and be able to cross-couple them? And you can replace an alcohol in a secondary position with methanol to introduce methyl. In this case, you can actually take 2 primaries and actually differentiate between one primary and the other one simply because it's methanol is one of the 2 different primary systems. Some cute things you can do, for example, is you can take peptides, and in this case, indeed, we're actually converting threonine over to a valine analog, and simply again by using methanol to make that change. Other ways you can start to employ this is to start to think about, can you actually use tertiary alcohols? Now, for our opinion, or the way we were looking at this, tertiary alcohols are incredibly prevalent within the world of organic chemistry. And one of the reasons is because there's so many different ways to make tertiary alcohols, and I'm just showing you a small range of some of the ways to do that. But I would argue tertiary alcohols are wonderful, but they tend to be the end of the road. We typically don't go many places from tertiary alcohols in general. Not obviously that's not comprehensive, but for the most part, that's where you end up. But we started to think about, well, maybe we could actually take tertiary alcohols now and actually be able to employ them to form quaternary carbon centers. So the idea here is, for example, take any range of different ketones, simply take alkyl lithiums and add them in, which we did. That generates these tertiary alcohols. And now by exposing these tertiary alcohols to methanol, you should be able to generate these quaternary carbons, which you can, in fact, you're now able to do that. And again, this is cross-selective to be able to do this exact transformation. Some other components of this which are important was we then started thinking about, well, what are some of the combinations you can actually use here? And it turns out there's a whole range of different combinations which are successful here. And this is basically just demonstrating some of the different combinations that you can actually employ together. But to this end, I'll sort of finish off by pointing out the tertiary with primary system. And we were able to show if you take, in this case, an alcohol that's got both a primary and a tertiary alcohol, and we know that using certain NHCs, we can actually accomplish selective adduct formation on a primary over a tertiary alcohol. If we take that now with a secondary alcohol, the question here is, can we couple the secondary with the primary but leave the tertiary alone? And in fact, when we actually do that, when we attempt that transformation, it actually works quite nicely. And in doing so, we do it with an unprotected tertiary alcohol. Now, the neat thing about this is we're generating one single bond from free alcohols in one flask. But the other thing is you can actually determine that this is reasonably general. Here I'm showing it both with tertiary and with secondary alcohols. You can do this cross-coupling to generate these adducts. But the nice feature I would argue about this is you still have a tertiary alcohol left over. And using that tertiary alcohol, you can then go on and do subsequent chemistry, and you can keep elaborating or iterating on this as you move along. You can start to utilize both primary with tertiary and keep building those up to generate a whole range of different types of molecules. Okay, so I'll finish off the chemistry part. I just want to obviously thank my group. This is a recent photograph of my lab. They're a phenomenal group to actually work with. I have to thank these folks for all the funding, both from the pharmaceutical side and obviously from the federal agency side. And the last 10 minutes or so, I wanted to finish off by, sort of talking about Larry. And obviously, as I've stated here, he's an amazing chemist, mentor, and role model. Slightly from my own perspective, I showed up at Irvine. This is a picture of Irvine back in the 1990s. This is when I showed up in Irvine around about this time frame. And the first thing I learned in joining Larry's group, that the group was just incredible. The group dynamic was second to none, in my opinion. It was just wonderful, amazing people. And I think a lot of that came from Larry. Larry was such an amazing advisor in so many different ways that he created a group who were just generally very happy. They were a very contented, satisfied, happy group. And because of that, we had a blast. We had just a fantastic time. This is just a couple of pictures to represent that, but it really was an amazing group. Just to point out how much fun this group is, while my talk has been going on, and many of them have been texting me, and it keeps showing up in the right-hand corner of my computer screen, and it's very hard not to laugh when I'm giving this talk because they keep texting me while the talk is going on. That's exactly the people that you're dealing with. But it really was phenomenal. But Larry is both a mentor and a role model as well as a chemist. There's many different lessons that I can say that I've learned, and I would argue that probably everyone who came through Larry's group also learned. And I wanted to share just a few of those in the last sort of few minutes. The first thing that Larry sort of taught me was that you have to educate and elevate everyone who comes through your lab. And recently we had a big party for Larry, and I made this analogy. It wasn't a very good analogy, but I called him the Henry Higgins of chemistry. And if you've no idea who Henry Higgins is, don't worry, no one seemingly knows who he is. But it was this character in this movie, this musical, basically, which effectively involved, it's called My Fair Lady. It effectively involved this professor who would take basically street urchin and turn them into wonderful, or at least capable human beings. And this is sort of what I felt Larry was like, especially for me, was he was able to take someone who really didn't know what they were doing, and he was able to help them and educate them and elevate them to actually become a decent chemist. And for me, I think Larry has done that for so many people, and it's just been an amazing to watch how he's able to do that. I know that analogy is not very good, but I actually had a conversation with Larry about, you know, how did he sort of focus on how he would actually run his group. And he once made this analogy to me, and it's always stuck in my head. And he said, it's a bit like spinning plate, the guy who spins plates, where the goal is to spin as many different plates as possible. And anytime there's a wobbling plate, that person will go over and basically spin it a little bit faster. If another plate wobbles, he goes over and spins that one. And Larry's analogy was that in your group, if you're having people who are having wobbles, those are the people that you should spend time with. The ones who are doing really well, you really don't have to spend that much time there. If anything, you might want to get out their way. And I always thought this was such a wonderful analogy about making sure that everyone succeeded, that no one was wobbling. And it's a very special way of thinking, which is very particular to Larry, and what makes him such a, I think, wonderful human being. The second thing is you have to train people based on their abilities. I won't go through this in all great detail, but this is the group jobs that were in the Overman lab when I was in the Overman group. I can say that I failed at all of the ones shown in red. Larry eventually put me on the worst job, which was butyllithium bottler, which is the simplest job you could possibly do. And I won't get into details, but I failed at that as well. And despite the fact that I failed at every group job I was ever given in Larry's group, he still didn't worry about that, and he didn't hold it against me. And he still would promote you and put you out there and help you to sort of develop. I can't remember what I actually ended up doing. I think I was probably put in charge of buying beer for a group meeting or something like that. But the bottom line was he was just someone who would really focus on the individuals, and based on their abilities, he would tailor his advice based on that, which for me was a tremendous lesson. The third one is you have to care for your co-workers equally. And this is something I think is really important, is that when I was in the Overman group, and I'm sure this was true for the whole time anyone was there, we never had any concept if Larry had favorites or not. You just couldn't tell, because he treated everyone so professionally and warmly, but equally. And this, I think, allowed the lab to sort of grow up together and really be able to, there wasn't any internal competition, there wasn't people who were trying to outdo each other. It really led to a very cohesive group. And to my mind, that was something that was so significant and a brilliant leadership style that is, again, I think is somewhat difficult to find, but also speaks to the character he actually is. Lesson 4, and this is one of my favorite things about Larry, is if you're going to do it right. There's no point in doing it if you're not going to do it right. And my favorite story around this is whenever I was working with Larry, I somehow managed to finish a natural product. I'm not quite sure how I pulled that off. But when we finished it, it turns out that natural product didn't have a name. We had to name the natural product. Now, the one that was known as unicellin, but the one that we had made didn't have a name, but it was found in New Caledonia, which means New Scotland. So I thought, wouldn't it be great? And I suggested we should call it New Caledonium because it sort of fits the Scottish theme and it's based on where it came. And Larry thought about it and he came back and said, it's okay, but what we should really call it is 7-deacetoxyl-cyanin acetate. And I tried to explain it doesn't exactly roll off the tongue, but ultimately I realized that was exactly right, because that is the name of the compound. If you have to name it, you have to name it right. And this is something that's always sort of stuck with me with the way Larry focuses upon problems and focuses upon his approach to almost everything, including golf, is if you're going to do things, do it the right way, because it will always pay off in the long run, which I think has been a tremendous lesson. Number 5, work hard for your people, especially your alums. And the conversation I always have about this is basically how I became an academic. But Larry is someone who, after you leave his group, still works very hard for all those different people. And I've seen this in so many different ways, in letters of recommendation he writes for so many people, how much he promotes people who've left his group. He doesn't have to do this, but he does it because he cares about those people. My story here was, I call it the Thinking Tuesday story, because when I was in the lab, Larry would always take Tuesday mornings off and he would call them Thinking Tuesdays. And we always assumed he was at home reading Jacks and thinking about new ideas. But at some point I realized the thoughts that he was actually having was, is this shot a 6-iron or is this shot a 7-iron? Basically, I'm pretty sure he was actually on the golf course on a Tuesday morning. But the point of that story was, through that realization, I started to think, what an amazing job that Larry has and academics have, to be able to have that freedom to sort of go off and think or do other things. So I became really interested in becoming an academic. However, along the way, before I became an academic, I was doing a postdoc, and at some stage when I was writing my proposals, I was really struggling. I was having a really hard time, and I basically decided that I didn't want to be an academic anymore. I was going to apply to industry, and I called up Larry, and he basically convinced me not to do it. And he basically said, look, you know, if you need an interview down the line, I'm happy getting an interview with companies, but I really think that you'd be happiest as an academic. I really do. And it was those types of conversations and discussions. And I always think it's so important when an individual cares that much about the growth of the people that they're working with and put in the time and the energy to do it is obviously very meaningful. And I always like to thank Larry for doing that. And then the last one is, and I think Larry said this at the beginning, you can work hard, but you always have to find the fun in life. And the thing I know Larry, he just told us he's just back from fishing in Mexico. He's probably out heading to the golf course straight after this. And, you know, Larry has always been someone who's had this tremendous balance in his life of loving science, but also been able to love life through all these incredible activities. And that's something that I've certainly learned from him, that you have to have balance with family, you have to have balance with science, but you also have to have balance making sure that you enjoy yourself and you get out there. And this is us playing golf in 2022 and also in 2023. I want to thank Larry. I also want to thank Joe for the opportunity to be able to provide this lecture today. And then ultimately, just to make sure I didn't miss anything, I just wanted to finish off by again dedicating this to Larry from the whole lab, but also the whole community. You really are a tremendous chemist, mentor, and role model. And you know, we really thank you for all the things you've done and for putting this autobiography together, which again I think has been just so wonderful to read. So thank you very much.
Thank you very much, Dave, really for this fantastic talk, and especially the last part. I think it was very enjoyable, and I don't think there's anything more to add at this point, unless Larry or Martin, if there's something that you would like to say.
Let me see if I can.
I think you're on mute, Larry.
Yeah, I explained when I was doing this that I retired before the pandemic, so my abilities on these or experience is not so great. But I really wanted to take this opportunity to thank David and Martin again for joining us and for their wonderful comments on this occasion. And thanks again.
Mm-hmm. And then, with this, I think I will officially now, unless Martin, sorry, if you want to.
I have nothing more to add, except for the fact that Dave was kind of describing his creative process also. And we need authors, of course, for 2027. And why don't you write a book yourself that we can then put on the market?
So I have to say, I was reading Larry's book, and he points out, and he said, you know, I look forward to the second half of Dave's career. I'm thinking, boy, I was kind of hoping I could get to the golf course faster than having to do this all over again for another 25 years. So I have another 25 years to go, Martin.
But we can do 2 volumes. I mean, there are people doing this. I mean, you can have a first volume on the first 25 years, and then we do a second one. Think about it.
Yeah.
Yeah. Again, thanks to everybody involved in this for setting this up, and also for the contribution, Dave, your talk science-wise, but particularly the last part. Thanks for doing this, also for Larry, and for this was a fantastic end to the whole event. Yeah. Thank you.
Then, what I would like to add on, and then also thank, of course, Larry himself for joining us here on this event, to the 2 amazing speakers, Martin and Dave, and of course also to the many viewers, like many of which really stayed until the very end. And I cannot or will not leave this meeting without a special thanks to Frau Eva Wille. Like, she is a member of the Life in Chemistry board, and she proposed the idea to me to do this collaboration. I think it was really a fun and nice joint project. So thank you, Eva. I think she's probably also watching. And then lastly, I hope that this symposium, the inspiring talks, have sparked your interest to read Larry's biography. So I'm also owner of this copy, and I can really recommend you to do the same. It's really an interesting really interesting read. So, and with this I wish you all a pleasant afternoon, evening, morning, wherever you are, and I hope to see many of you at the next EurJOC virtual symposium. Thank you. Bye bye.
Thank you.
Bye.
Bye. Thank you.